Okay, before we begin, I just want to confirm that you guys can hear me clearly and can see my screen. So please just type in the chat that you can hear me. Okay, perfect. Okay, cool. Okay, even on YouTube, if you guys can just confirm that you can hear me, that would be great. Perfect. That's great. Okay. Okay, assalamu alaikum and good morning to everyone. Welcome to the inaugural lesson of grade 10 maths. Okay, my name is Abdullah Ali and I will be your guys' tutor, hopefully for the rest of the year, right? Today's lesson, we're going to be starting with algebraic expressions. Please forgive any first lesson jitters or any technical issues, but we're gonna work through them, right? But yeah. Okay, is there anything else? Yes, if you have any questions, okay, please, you can utilize the chat. You can also utilize the Q&A feature, okay, to ask those questions. Okay, cool. Anything else? No, for now, that's good. Okay, so grade 10 algebraic expressions, let's get started. Okay, so we're going to start off with going through some basics first, okay, before we get to the expressions. Let's just see. Yeah, okay. So we're going to go through the difference between non-real numbers and real numbers, okay? So the first thing we're actually going to define, so we have two different ones, real numbers, non-real numbers. The first thing we're going to define for you to understand is non-real numbers, okay? We're going to take it simply. So non-real numbers are defined as imaginary numbers that are not real. It is any number that has a negative inside of a surd. So basically, any number that has a negative inside of a surd, simply put, not more complicated than that, is defined as a non-real number. Any number that has a negative within a surd is a non-real number. What is a real number? Everything else. Okay, no need to complicate it. A non-real number is a number with a negative inside of a surd, and a real number everything else. Okay, thereafter we further break down what a real number is. Okay, a real number is separated thereafter into a rational number and an irrational number. Okay, a rational number and an irrational number. Okay, so we're going to define, let's look at the definition of a rational number. A rational number here is defined as a number that can be written as A over B or a fraction. Actually, this represents a fraction. Okay, where B is not, B cannot be equal to 0, of course, because any denominator that's equal to 0 makes the term undefined. Okay, maybe that doesn't make as much sense. Let's define an irrational number first. Okay, so before we get there one more time, I just want to clarify. We discussed real numbers, non-real numbers, two separate categories. When we discuss rational and irrational, we are now within the real numbers. Okay, maybe let's move this to the side, so that we know that that's different. Okay, non-real numbers and real numbers are different, right? And now under real numbers, we're talking about rational and irrational. So we went through rational. Let's talk about irrational. So irrational basically states here, it is a non-recurring and non-terminating decimals, which basically means they give the example as √5 and pi. So when we put √5 in our calculator, okay, we get a decimal answer of 2,236067977 ... So it might end at 77, but actually that's just because all of your that's the memory that your calculator has, right? But actually this number goes on till infinity. It has many different numbers. So too is the same with pi. Okay, when we put pi in our calculator, normally we memorize it as 3.14, but it's actually 3,1415926 ... So those numbers go on forever. We call them irrational. Irrational numbers are numbers that we don't know the end of. We don't know all the values, all the digits of that actual term. An example is root 5. It's decimals, non-terminating decimals. They go on till forever. Okay, we can never determine the complete value of it. Okay, can't see the full screen. Try refreshing it, like maybe close and open or rejoin, or like just close the app, open the app, something like that. And I've heard that that works. Okay, so those are irrational numbers, whereas rational numbers are numbers that we actually know the entire value of. An example is 2. There's nothing more to 2. Okay, 2 is 2, right? We know its entire value. That's all it is. Let's look at another fraction, 3/5. 3/5, if we write it as a decimal, is 0.6. That's it. It doesn't have any non-recurring decimals. Okay, so it is not irrational. It is a rational number. We know the value, the entire value of that number. 20.5. Okay, again, it's a decimal, but it's not non-recurring. So we can write it as a fraction. Yeah, okay, hope that makes sense. Irrational numbers, we can also write it as an improper fraction. But again, when once we convert it to the decimal, to distinguish between the two, the main thing is to understand that it is non-terminating decimals, meaning they continue forever. Okay, further, under real numbers, under rational numbers, we have 3. We have integers, we have whole numbers, we have natural numbers. Okay, again, this must be some sort of revision, but maybe some people have this confused as well. So we're going to start from the bottom. Natural numbers are how we naturally count. Okay, so if you're playing hide and seek, I hope nobody's playing hide and seek at that age, but anyway, if you're playing hide and seek, how do you count? Nobody starts and counts 0, 1, 2, 3. You count from 1. Naturally, whenever you're counting, you count from 1. So natural numbers start at 1. We have whole numbers, okay, which are all the natural numbers, including 0. Okay, remember, whole numbers, as the name states, they are whole, meaning decimals like 3.5 are not whole numbers. Okay. So your whole numbers are your natural numbers, just including 0. Thereafter, we have integers, okay? Integers, right? They include your natural numbers as well as negative numbers. Okay, so integers include your negatives. How do you convert recurring decimals to rational numbers? Okay, we'll get there. I don't think you are... Are you required to in grade 10 to convert the recurring decimals to numbers or to fractions or whatever? But we'll get there. We will eventually get there. I'm not sure in this lesson, but we will, if it's in your syllabus, we will cover that. Okay, please explain pi. Okay, then we will do it. I'll make sure to make a note of it and we will do it. Okay, but yeah, for now, these are the basics of just please explain. Oh, pi, like actually pi. I was so confused for a second. Okay, so pi is a number. It's like a ratio created by some genius. We don't really care unless you're a mathematician, but pi is a value that if you input it in your calculator, right, it gives you, like I said, it's a ratio created, right, 22/7. And it's a ratio that gives you decimals. Okay, so in this case, the value for pi, which again is found on your calculator, is 3.14159264 and so on, right? It has non-recurring decimals, and pi is one of those irrational numbers that are non-recurring. Okay, hope that makes sense. Okay, on the right hand side is a little diagram explaining the different types of real numbers. Okay, will be a lesson factorizing binomial trinomials. Yes, we should get to that in this lesson. Okay, let's move on. That was a revision of our real and non-real numbers. Then we're going to move on to estimating surds, okay, which is the next part. But before we talk about estimating surds, we're going to talk about our perfect squares and cubes and ones that you should know. Okay, this table is generally a list, and I would say for perfect squares, you should go up to 11 and 12. Okay, but your perfect squares for 1 is 1, for 2 is 4, 3 is 9, 4 is 16, 5 are 25, and so on. You should know those, right? You should by heart those. So the square roots, that is correct. Yes, yes, that's correct, guys. Okay, so, okay, and then, and as well as your perfect cubes, 1, 8, 27, 64, 125, and so on, right? Square roots, a surd is represented by this guy. Okay, so your square roots, your cube roots, okay, because we can deal with cubes as well. Okay, sure, go back to the numbers. Okay, one more thing I think, I don't know if I mentioned, but if you'd like to take notes in this lesson, you may feel free to. However, the PDF that we do in this lesson will be sent to you guys on WhatsApp afterwards. Okay, so just explain to me, like ask me exactly what you what you need explained, and I can go through it. In the meantime, I'm going to carry on with. Okay, most people call it square roots. That's fine. Okay, like I said, surd refers to that symbol, okay, which is square root, cube root. Are we going to do square binomials? Yes, indeed. Most likely in this lesson. Okay, find the, okay, so estimating surds, we have certain steps, okay, mainly one step that we're going to use to determine. So they want you to estimate, what are we doing here? Sorry, just give me 1 second. Brain fart. Okay. So, okay, we should go through it today. Okay, find the perfect square or cube before. Okay, so when it comes to estimating surds, the main question is between which two integers, okay, does root 21 lie? Okay, so that's how they could phrase the question to you. Between which two integers does root 21 lie? So the way we are going to determine this, okay, because obviously this is a square root, right? If there's no number on the surd itself, on the root, surd root, then we assume that that number is the 2, and it is therefore a square root. So if we have to say square root 16, can somebody give me the answer to this, please? Okay, 4, quick, like that was the first one, perfect, right? So 4, right? So the answer to square root 16 is 4. The reason that we know that is because 16 is a perfect square. Okay, now since 16 is a perfect square, we can simply, we've memorized it at this point, when we square root it, we know we get 4. However, 21 is not a perfect square. So therefore, when you say square root 21, nothing comes to mind because, again, it is not a perfect square. So what we need to do is we need to follow this step that says find the perfect square or cube, depending on what we're dealing with, before and after the number in the surd. Okay, so basically, we have root 21. The perfect square after root 21, again, we're dealing with 21, okay, would be root 25. That's the perfect square after root 21. The perfect square before root 21, root 16. Okay, we know the value of root 16, that's 4. We know the value of root 25, that's 5. So therefore, root 21 lies between which two integers? Integers 4 and 5. Binomial starts in ATF, yes, most likely in this lesson. We're going to do cubic expressions. Hopefully we get there. Okay, so I hope that makes sense. Estimating surds. okay, between which two integers does root 21 lie? What you need to do is simple. You need to find the perfect square or cube before and after the number in the surd. So in this case, our number in our surd is 21. So what's the perfect square after? 25. So root 25. What's the perfect square before? Root 16. Okay, and then we get 4 and 5. So between 4 and 5 is the square root. Between which two integers does root 21 lie? Between 4 and 5. If you have to use your calculator and put root 21 in your calculator, you'll see that you get an answer of 4.58 whatever. That means that your answer is correct. It lies between 4 and 5. Okay, but obviously you're going to have to show how you got there. Let's do something like root 7. Okay, so root 7, what's the perfect square that lies before root 7? Root 4. You get root 7. And after root 7 is root 9. So this is equal to 2. This is equal to 3. So this guy is somewhere in between. So root 7, okay, we could say root 7 is greater than 2, but less than 3. Okay, but because it lies in between the two. So square root 21 remains unknown. Yes, because that's not what the question was. The question is, between which two integers does root 21 lie? So your final answer would be between 4 and 5. Okay, let's do one with cube and then we can move on. So let's talk about cube root 30. So cube root 30 is here. We need to find the perfect cube after 30 and the perfect cube before 30. So let's look at our cubes. Before 30 would be 27. After 30 would be 64. So cube root 27 and cube root 64. So cube root 27 is 3. Cube root 64 is 4. So therefore cube root 30 lies between 3 and 4. So cube root 30 is greater than 3 but less than 4. Someone has their hand up. Just rather ask your question in the Q&A or the chat. Okay, so yes, cube root 30 lies between 3 and 4. So it's in between the two, and that's how we determine it. Okay, estimating surds. All right, let's move on. Let's do a revision on rounding off. Okay, so rounding off, remember, we learned this probably in grade 8, if not before. If the last digit is from 0 to 4, the number stays the same. And if it's from 5 to 9, we round one up. Okay, maybe it won't make sense. Let's do our example and then go back to that. It will make more sense. So when we have a number 15,721, they want us to round it off to the nearest 10. So remember, if we have to go back to grade 8, we have, okay, these are our 10,000s. This is thousands, hundreds, tens, units. So the nearest 10, okay, means that we have to round it off to the nearest 10. Okay, so 2 is actually going to be our last number. It's either going to change to 3 or it's going to remain as, like you guys said, 0. Okay, so the 2 represents 20. So to the nearest 10 is either going to become 20 or it's going to become 30. So how do we determine what it's going to become? Smart people in the chat, is we follow this rule. If it's from 0 to 4, what's from 0 to 4? The number after. Okay. If the number after, in this case, our tens column, is from 0 to 4, it's going to remain the same. If the number after is greater than 4, meaning from 5 to 9, we round one up. So in this case, okay, it's going to become 1572. Okay, 157. And we can see that the number after is 1, and therefore it's between 0 and 4, so it's going to stay the same. So it's going to stay as 20. Then we look at the next one, nearest 100. So the 100 column is here. So now we look at the number after the 100. Is it from 0 to 4 or is it from 5 to 9? it's from 0 to 4. So it's going to change to 15,000 and everything else becomes a 0. 700. The nearest 100. Remember, hundreds go in 100, 200, 300, 400, 500, 600, 700, 800. So this is either going to be 700 or it's going to be 800. Because the number after is less than 5, it's going to stay as 700. Let's look at the next one. 1,000. 15,721. Here's my thousands column. I look at the number after. Is it between 0 and 4 or is it greater than 5 but less than 9? It's from 5 to 9. So we need to round one up. So this 7 is going to change. Sorry, that 5 is going to change into a 6. Okay, so the nearest 1,000 is either 16,000 or 15,000. But because that 100 number or the number after the 1,000 is from 5 to 9, you guys are correct. We're going to round it up to 16,000. Okay, so that's just revision of rounding off. I am assuming that most people are extremely clued up with rounding off, and we've been doing that. We've been doing it for years at this point. Now, let's talk about just decimals. I just wanted to revise some decimals. We won't do many. Don't worry. I know some of you are tired of this already. Round off the following, just because decimals, maybe we might see it as more complicated, even though it's the same concept. Round off the following to 3 decimal places. So let's take E. 3 decimal places simply means that we need to have 3 numbers. Okay, so when we need to have 3 numbers after the comma, we need to look at the 4th number to determine whether the 3rd number is going to change or remain the same. Everything else is going to disappear. So in this case, we have 6, 3, 2, 4, and then there's a 5 after. So because there's a 5 after the 4, this 4, it's between 5 and 9. This 4 needs to go 1 up. So it's going to become 6, 3, 2, 5. Let's look at this guy. 4 decimal places, I'm going to say 3, 4, 5, 4 decimal places, I need those ones. And this is the number I look at. Okay, so this is a 9. It's greater than 5. So this 9 is going to change the number before it. The number before it is also a 9. So it's going to change the number after as well. Okay, correct. So we get 0, 4, 4. Because they said 4 decimal places, this 9 became a 0, so we need to put it as a 0. Very good. I'm glad that all of you put the 0. That's excellent. All right, let's look at this last one, 2 decimal places. 1361, 72, there's my 2 decimal places. So therefore, I need to look at this number after. This number after is a 9. It's between 5 and 9. So I need to change the number before it 1 up. I need to round it 1 up. So it's going to become 73. 2 decimal places, guys. So not 730. 730 would be 3 decimal places. Yes. We're going to move on to algebraic expressions right here, guys. I apologize. But these are some basics that are in your syllabus, that are in the annual teaching plan for GDE. So we have to go through it. Okay. So yes, rounding off and decimals as well. Now let's move on, okay, to more grade 10 work. Okay, we're going to move on to algebraic expressions, all right? So firstly, we're going to go through some terminology, okay? So let us write 5x cubed. Okay. So the first terminology that we're going to go through is known as the numerical coefficient, or the coefficient, which is the number in front of the variable. Okay, how are you going to define something without defining variable? Let's look at a variable. A variable is an algebraic letter used to represent something that is unknown. So x is a variable. It's a letter. Okay, let's use different colors. So this is our variable. And then the numerical coefficient is something that precedes the variable. It's one before the unknown variable, the number before the unknown variable. Okay. Then we have a constant, which is a numerical term. Okay, we'll get to that in like an actual term. So let's maybe add on to this. 5x cubed plus 2. In that case, okay, we could refer to this 2 as a constant term. It's a numerical term. It has a value that we know. It's not unknown like a variable. Okay. An algebraic expression is a mathematical expression made up of one or more terms separated by addition or subtraction. So basically what I have, what color can we use? Orange. What I have here, this is an algebraic expression. It is a mathematical expression made up of one or more terms separated by addition or subtraction. So in this case, I have one term, two term separated by an addition. This is clearly an algebraic expression. How would that differ to an algebraic equation? The difference between an expression and an equation is that the equation has an equal to sign, but an expression doesn't. So if I had to say 5x cubed plus 2 is equal to, let's just say 0. In that case, now I have created an equation. Okay, does that make sense? Okay, so that's simple differentiation between the two. Let's talk about a polynomial. Okay, so you get like monomial, you get binomial, you get trinomial, and you get polynomial. So let's just look at polynomial, then we can just briefly revise the others. Polynomial is an algebraic expression where the exponents on the variables are natural numbers. Okay, cool. Monomial example, 4 or 2a squared bc is one term. Binomial example 6. Okay, so basically the nomial term is representing the mathematical expression. Poly, mono, bi, and tri represent the numbers. So in an algebraic expression, if it's a monomial, it has one term. If it's a binomial, it has two terms. If it's a trinomial, it has three terms. How do we distinguish from one term to another? They have to be unlike terms. Okay, so if you have to look at this, like what distinguishes this as two terms? The fact that it's unlike. We have 6x and 2y. We cannot add those two together. Yes, these notes will be uploaded, definitely. Okay, let's not get too fancy. Okay, not necessarily, each term does not necessarily have to have a variable. It could even be just a constant number, and that's regarded as a term. But as long as you have two terms which are unlike terms, they are two separate terms, we call that a binomial and trinomial, etc. Okay, cool. Degree is the highest value of the exponent of a specific variable in an algebraic expression. Okay, this term is not so important, but good to know. Okay, so for example, in the 7x cubed minus 3xy plus 8x to the 6 plus 4 has the 6th degree in x and first degree in y. So it's the highest exponent. Okay, let's talk about like terms. Okay, 6. Okay, let's talk about like terms, right? Like terms are terms with the same variables with the same variables with the same exponents, the coefficients made of. Okay, so like terms, again, simply they have the same variables. Oh, okay, I got you. They have the same variables. So if I have to have 6a and 4a, the coefficient can differ, but as long as my variable is the same, this is what I would refer to as a like term. Remember, the order of it doesn't matter. So if I have 3a squared bc and I have 4bca squared, these are like terms because they have the exact same set of variables, just in different order. It's multiplied. So remember, in multiplication, it doesn't matter, right? What are not like terms are 3a squared b and 4ab squared. You may think that these are like terms, but remember the exponent is for each individual variable. So here the exponent is for A, here the exponent is for B. So those are technically different variables. Different variables creating two unlike terms. Are you going to give us some sums to do on when we're done? There will be oftentimes, I'll try in every lesson to add the sums that you guys may do. We're still trying to figure out a way to sort of work together with you guys, like to give you guys work and then get feedback, whatever it is. So I'll confirm on that with you at another time. Does like terms cancel each other out? So like terms don't necessarily cancel each other out, but like terms you can add and subtract. So for example, if I had 6a and 4a plus 4a, I could add these two to get 10a. I add the coefficient. However, these two I cannot add because they are not like terms. Let's look at unlike terms. Unlike terms are terms where variables are different. Example, 2x, 2x squared, and 3xy. Different. This is not geometry, this is algebra. Simplifying algebraic expressions, follow Bodmer's rule, but can only add or subtract like terms and write your answer with variables in alphabetical order and terms in descending order of your powers. That's important. Descending order of your powers means you write the biggest power first. Okay, we're getting there, guys. I'm just going through the basics, and immediately we're going to start multiplying monomial by polynomial, binomial by binomial, dots, squaring binomials, binomial by trinomial, mixed questions. We're getting there. Okay, I'm just starting off with basics. Biggest power first. Okay, so let's look at this. We are going to add up our like terms, write it in order of descending power. So here we have BCA, here we have ABC. These are like terms. They have the same variable. Here we have A squared BC. Here we have BCA squared. These are like terms. They have the same variable. They just rearranged. Okay, and in multiplication it doesn't matter. What about this guy? CAB is the same as ABC. Okay, again, we want to do it in alphabetical order. So I'm just going to rearrange it. I'm going to have 6ABC minus 7ABC minus 3ABC plus 4A squared BC plus A squared BC. So when I add like terms, I go for my coefficients. I keep the variable the same, but I add the coefficients. So 6 minus 7 is -1. -1 minus 3 is -4 ABC. This is 4 plus 1, essentially, because again, I work with the coefficients. So 4 plus 1, that gives me plus 5A squared BC. Aiden. Choke man. Okay. Monomial by a polynomial. Use the distributive law. So monomial is a term, is a algebraic expression with one term. Okay. So in this case, our monomial, I keep on saying monomial. Our monomial is 2A squared. By multiplication, a polynomial, a term with multiple terms. So use the distributive law. Okay, so that's exactly what I'm going to do. Distributive law states that I take the multiplication outside and multiply it by each term on the inside. So I'm going to say 2A squared times 3A squared plus, because it's positive 2A squared and positive 4AB, plus 2A squared and 4AB minus 2A squared, because it's, remember, it's positive times negative, minus 2A squared times A cubed C. Yes, that's correct. At this stage, geometry is like Euclidean geometry, analytical geometry, all of those. So now I'm going to multiply this out. When I multiply these terms, okay, I multiply coefficient by coefficient and variable by variable. So I have 2 times 3, which is 6. A squared times A squared, if we remember, at some point we will get to doing revision of exponents. A to the power of x times A to the power of y is equal to A to the power of x plus y. So in this case, I'm going to say A to the power of 2 plus 2, which is A to the power of 4. No, you don't have to put it in brackets. You don't even have to write that step. You can skip it. I'm just doing it for the sake of understanding, for explanation, sorry. So you can do it straight away. And at this point, I expect most of you to be doing it straight out. Then again, I'm going to say coefficient times coefficient. So 2 times 4, which is 8. A cubed B minus 2. This is A5, eh? Not 2 times 3. When you have same bases, different exponents, you add the exponents. And there's 1C, I believe. If there's anything incorrect, just correct me, please. But that's how you multiply a monomial by a polynomial. Okay, using distributive law. Let's do binomial by binomial. Okay, so most of you have probably learned the FOIL method. Isn't 2 times 2 4? This isn't the 2, it's my lovely A. Try and write my A's like a human. Okay, a binomial by binomial. A binomial by binomial, we use FOIL. First out is, I don't know who put them up. Nobody does that. I hope nobody does that. First, outer, inner, last, which is what FOIL stands for. So what is a binomial by a binomial? Let's look at this example specifically. We have 2x plus y. Okay, two unlike terms. Okay, two unlike terms as an algebraic expression multiplied by two unlike terms again. That is now when we use FOIL. We multiply the first terms. Outer, we multiply the outer terms. Inner, we multiply the inner terms. Last, we multiply the last terms in each bracket. Should I go through that one more time? FOIL. FOIL is what we use. Okay. FOIL and products, the same thing. Yeah, it is. It's basically, it's like distributing, but you're just distributing both essentially. It's called FOIL. It's a multiplication method where you multiply the first, the outer, the inner, and the last in a binomial by binomial. Okay, so first in each bracket, we have two different brackets. The first term in each bracket is these guys, 2x and 3x. Outer is the outer ones, the ones on the outside. So 2x and 4y, those are the outer ones. Inner, y and 3x, those are the inner terms. Last in each bracket, y and 4y, minus negative 4y are the last terms. So let's multiply them. Let's do the first one. First is 2x times 3x. 2x times 3x, that gives me 6x squared. One second. Okay. 6x squared okay, so yes, first 6x squared, sorry for that. Outer is 2x times negative 4y, 2x times negative 4y. We get negative 8xy. Inner plus y, positive 3x, you get plus 3xy. And last, y and negative 4y, you get negative 4y squared. Okay, I will slow down. Okay, so in that case, you have 6x squared. These are now like terms. So we need to simplify these like terms. So negative 8xy plus 3xy, those are like terms because they have the same variable, xy and xy. Okay, negative 8 plus 3 is negative 5xy, and then minus 4y squared. So multiplication of a binomial by another binomial, we use the FOIL method, okay? And we multiply the first, the inner, the outer, and the last. Nice, well done. Let's do another example quickly. Okay, we're going to do FOIL. First, outer, inner, last. So let's do the first. The first two in each bracket. That gives me 3x squared. Let's do the outer ones. That gives me positive 9xy. Let's do the inner. That gives me negative 2xy when I multiply them. Let's do the last. That gives me negative 6y squared. In order to simplify this, I simplify my like terms. So that's 3x squared is not like with anything. However, xy and xy, those two are like. So 9 minus 2, that becomes positive 7x y minus 6y squared. Okay, binomial by binomial using FOIL method. If you're getting confused, rewatch later on to try and get that same explanation. Let's talk about squaring a binomial. So squaring a binomial essentially is when we have something like this. We have a binomial and then you square the whole thing. Well done. So in this case, what not to do is you can't say p squared plus 2r squared. This is completely incorrect. You cannot do that. Okay. What you need to do is you need to follow the shortcut. Okay. So again, this is basically p plus 2r, open brackets, p plus 2r. It is two of the same brackets because you are squaring it. Okay. So the shortcut is simply when you have a plus b squared, a binomial squared, what you need to do is follow the shortcut. Square the first term, a squared, plus 2 times the first term times the second term. This is a shortcut, right? Plus the second term squared. First term squared plus 2 times the first term times the second term plus the second term squared. Yes, you could do FOIL, whatever FOIL is, right? However, you could also take this shortcut and skip one step. So let's do that exact thing here, keeping this in mind. So here's the explanation. Square the first term, multiply the first term by the second term and double it, and square the last term. So let's follow that step. Square the first term. I get p squared. Okay, let's do it in brackets. Multiply the first term and the second term. So p and positive 2r and double it. So I say 2 times that. Okay. And thereafter, square the second term. So 2r squared. So here we get p squared. Here I'm going to get 2, actually 4, because it's 2 times 2. 4pr. I think, does r come first? Whatever, it's not English. Plus square the number, square the variable, 4r squared. Is there ever a time where you don't open the brackets, or do you always have to open them? Okay, so that's a good question. There are times where you don't have to open the brackets. Okay, that's mainly in what we call factorization. Okay, which we will get to in the next page. What we are learning now are just algebraic expressions firstly, and simplification of algebraic expressions. Simplifying algebraic expressions. Okay, this is when you will open them. However, when it comes to factorization, that's a different case. Okay, in those cases, many times you do not open the brackets. Okay, so squaring the binomial, done. So let's do this next one. I'm going to follow the steps. Square the first term. Do the variables have to be in alphabetical order? Not necessarily. If you have a really fussy teacher, you can ask them if they really want it to be, but you won't get marked incorrectly if your variables are not in alphabetical order. It's just good practice to do it. So I'm going to square the first term, plus 2 times the first term times the second term, plus I'm going to square the last term. So 3a squared, again, you can skip the step if you'd like. 3a, this time it's minus 4b. I have to take the sign with it. The second term here is negative 4b. Plus this last term squared. What am I doing? The last term is 4b. Then I simplify. I get 3. No, I don't. Remember, again, we'll get to revision of exponents at some point. But when you have x times y squared, the whole thing is squared, you will square each one. You'd like distribute that exponent to each one. So this becomes x squared times y squared. Okay, so similarly in this case, I need to square the number as well. So that's going to become 9a squared plus, I'm going to multiply all my numbers here. Positive 2, positive 3, and negative 4. That is positive 6 times negative 4. That becomes, oops. It actually becomes negative 24, I believe. Then I'm going to multiply my variables, a times b, ab, plus I square 4, which is 16b squared. Okay, okay, you guys are correct. I see where you're coming from. I'll explain it in a second. Negative 24. Okay. I'm not sure I understand what you wrote. You could just say first times first, 2 times first times last time last, an easy way to remember it. Yes, correct. That's true. Are these from X Factor textbook series? No, they're not. I utilize some CAPS textbooks. Maybe at times I might use X Factor. I use Science Clinic as well, and Classroom Mathematics at time, whatever. I'm doing factorizations with highest common factor. If we get to that, we might not today, but we'll sort it out. I'll speak to you guys at the end. Okay, just one thing I want to just clarify here quickly. This here, by the way, okay, before we determine the sign, actually it's negative 4b squared. Negative 4b squared. The plus we can put either way because it won't make a difference. If there had to be a minus afterwards, it would use it would change to a minus if it needs to be. But here actually there's one correction. It should be negative 4b squared. Okay, it does not affect our answer, but we have to be specific about that because yeah, it's not going to change the answer, but because it's a negative, the second term is a negative, and you're squaring the second term, you have to put negative. Okay. However, when you square negative 4, if you put it in brackets in your calculator, open brackets negative 4 squared, you get a positive answer. You get positive 16 because technically it's negative times negative, which gives you a positive overall. So you get positive 16b squared. Yes. Okay. So I find FOIL method easier. That's perfectly fine. You don't have to do this. Why is it 2 times a times b? That's the method that you have to follow for the shortcut. You don't have to do the shortcut. For the shortcut only works for squaring a binomial, not like a different binomial to a different binomial. This is just shorter, faster. Exactly. You skip out that one step. Okay, perfect. Okay, cool. So that was squaring a binomial, okay, with the shortcut. Okay, now we're going to start off with products. We are going to start off with the difference of 2 squares. Okay, that sort of ties into factorization. And we're most likely going to end on this. Okay, so the difference of 2 squares, right? The 2 binomials are the same except the sign in 1 plus plus plus. The other is a minus, the outer and inner side. Then okay, so what difference of 2 squares is in short, we can call it dots. Okay. It is essentially what it says. The name for it describes exactly what it is. The difference, which is a minus sign, of 2 squares. You have 2 squares. Okay, so I'll give you an example of what one looks like in a second. Okay, so if I have 16 minus 4, 16 minus 4. So 16 is a square. 4 is a square, and I have a difference, meaning I have a negative. So this indicates the difference of 2 squares. Okay, that's just what it looks like. Let's look at this. Okay, this example goes backwards. Okay, okay, it's fine. We don't have to go through that. Let's go through this. Okay, we can make our own example first, actually, using the numbers. Now I'm going to introduce variables. If I have 16a squared minus 4b squared, okay, 16 and 4 I kept the same, so they are perfect squares, definitely. And I've added variables a squared and b squared, so these are also perfect squares. All right, so with the difference of 2 squares, the ruling is when you have a squared minus b squared, okay, which is the difference of 2 squares, you should always simplify it. You can factorize it with two brackets, and 100% of your time, your brackets are going to be a minus b. So the first term minus the second term, and the first term plus the second term. Everything powered to an even square. That's very good. Correct. Okay. So the first term minus the second term, and the first term plus the second term. So in our case, if we had 16a squared minus 4b squared, we could simplify this to first term. Okay, so look here, we went from a squared to a. So to get this bracket, you have to square root it. So the square root of 16a squared is 4, and the square root of a squared, is a. Minus square root of 4b squared is 2b. Then I'm going to have 4a again plus 2b again. So we square root each one, and we add and subtract them respectively in each bracket. Okay, then we have something like this, where now we need to be able to see, the thing is, we need to be able to judge, do we have perfect squares? And yes, here our numbers are perfect squares, like 25 and 49. X squared is a perfect square, definitely. What about y to the power of 4? What if you put it as a plus b, a minus b? So you cannot leave it. So this is basically like a formula to tell you that every time that's the formula you follow. But in the specific example, you have to use the specific values and variables. Okay, now this one here, y to the power of 4, is that a perfect square? Yes, it is a perfect square. Like the person said in the chat, everything powered to an even square is going to be a perfect square. So therefore you have, in this case, remember, this is our a squared, this is our negative, this is our b squared. So we need to convert a squared minus b squared into a minus b, a plus b. Okay, so in this case, a is going to be 5x, because I square rooted 25 x squared. 1 second. Give me 1 second, sorry. Okay, so I square rooted it, it becomes 5x. The second one is 7 y to the power of 2. Okay, square rooting y squared. Remember, again, this is an exponent rule. It's a fractional exponent. This becomes y to the 4 over 2, which is y to the 2, essentially. Okay. But yeah. Okay, so let's complete this. Then we have the same thing, but plus. Okay, I hope that makes sense. Okay, so let's end it there. We are already very late. From next week, we will continue binomial by trinomial, mixed questions, as well as factorizations and more factorization. Okay, with regards to, I know like some of you might be writing tests next week or written tests previously. The main objective for now, obviously the tuition started later in the term. The main objective for now is to try and complete all the work for your guys' term 1 examinations. And yeah, we will be communicating with you with regards to any updates. These will be uploaded to the WhatsApp group latest by tonight, as well as the YouTube video will be uploaded. You will have the link for it in the group, and you guys can watch it one more time. Okay. Will dots we work with cube? Cubes, no. Dots will not work with cubes. Cubes are different. We will go through that in the next section. Should we first do exponent laws first? Perhaps that's something I'll consider in the next lesson. Okay. I mean, no problem. Okay. So yeah, I hope you guys benefited from this. It's our first lesson. So we will be working going forward and better everything as we go along. And yeah, any updates or anything will be communicated to you guys. These notes will be uploaded to the group. And I think that's about it. Cool. So I will be ending it now so that I can start the next lesson. But thank you guys so much for joining. I hope that it helped. And I'll see you guys next week, inshallah. Jazakallah. Assalamu alaikum. And thank you and goodbye.